Section: Introduction. In this section, we discuss the importance of extracting motion properties from scenes, such as optical flow and occlusions, for applications like video filtering, action recognition, and motion prediction. We note that these motion primitives are crucial for enhancing video generation and are significant in fields like robotics. Consequently, improving motion estimation is a key focus in computer vision, with optical flow and occlusion estimation being central challenges. Typically, optical flow estimation relies on supervised learning from labeled data, but annotating real-world scenes is costly, leading to a dependence on synthetic data. While methods trained on synthetic data perform well in real videos, they miss out on recent advancements in self-supervised learning and face challenges due to the differences between synthetic and real environments. Self-supervised methods often use photometric loss, which involves learning to match features between frames. However, this approach can be weak because correspondences can be unclear, especially in complex scenes. Current state-of-the-art methods use various techniques like nearest neighbor searches or additional regularizations, but these can be limited when the underlying assumptions do not hold. We propose a new method called Opt-CWM, which extracts self-supervised flow and occlusion estimates without relying on these heuristics. Our approach is based on counterfactual world modeling, CWM, which generates estimates from a pre-trained model. CWM uses a two-frame masked autoencoder that learns to predict the next frame based on limited information from the current frame. To improve CWM, we introduce two key innovations. First, we create a learnable neural network that generates counterfactual perturbations tailored to specific points in the scene. Second, we train this generator without needing labeled data or heuristics by applying a generalized version of the asymmetric masking principle used in the base model. By connecting the flow outputs to a new sparse flow condition predictor, we optimize both the predictor and the perturbation generator together. This joint optimization helps refine the predictions and enhances the performance of our method. Our results show that Opt-CWM outperforms existing self-supervised motion estimation methods and even some supervised methods in challenging scenarios, indicating a promising direction for future research in extracting various visual properties. Section Summary. In this section, we discuss the importance of accurately estimating scene motion properties for video understanding and introduce our method, Opt-CWM, which enhances counterfactual world modeling by using a learnable perturbation generator to improve flow and occlusion estimates without relying on heuristics. Our approach outperforms existing self-supervised and supervised methods, demonstrating its effectiveness in real-world scenarios and paving the way for scalable extraction of various visual properties. Section: Related Work. In this section, we discuss related work in flow estimation. We start with supervised flow estimation, where methods like RAFT treat optical flow as a dense regression problem, learning from synthetic datasets. These methods use specialized architectures designed for optical flow, incorporating strong biases and regularizations to learn effectively from limited data. While they perform well in many situations, their dependence on synthetic data and specific architectures restricts their adaptability. This is why our self-supervised approach, Opt-CWM, which can be trained on an unlimited number of real-world videos, can surpass supervised methods in certain important scenarios. Next, we look at self-supervised flow learning methods, such as SMRF, which optimize photometric loss to learn dense visual correspondence. However, these methods often rely on a mix of heuristically chosen regularization losses, like ensuring smooth flow, to achieve decent performance. This reliance on heuristics can lead to failures in complex dynamic scenes, especially with large time gaps. In contrast, Opt-CWM does not depend on such heuristics, as the quality of flow extraction is directly linked to the learning objective. We also explore methods that enhance self-supervised flow with features from visual pre-training. For instance, the Dodwo method uses features from Dino v2 to compute correspondences for photometric loss, allowing these methods to work with larger video datasets like kinetics, thus improving their performance and generalizability. However, even with strong image features, photometric loss remains a weak constraint, necessitating heuristic regularizers. Opt-CWM, which avoids scenario-specific heuristics, performs better than these methods. Point tracking, which relates to flow and occlusion estimation, is mostly addressed through supervised or semi-supervised methods, making it less relevant to our work. However, some recent self-supervised approaches use pre-trained representations to find temporal correspondences, extracting point tracks through consistency objectives like cycle consistency. The current leading method in this area, GRMW, builds tracks based on frame pair predictions using cycle consistency, serving as a baseline for our Opt-CWM. Lastly, we mention the TAP-VID benchmark, which provides essential metrics for assessing motion estimation systems in real-world videos. This benchmark is crucial for testing advancements in motion estimation against the complexities of real-world scenarios, which are often not present in synthetic benchmarks. Although initially aimed at supervised point tracking, recent self-supervised tracking works have started using TAP-VID as a key benchmark for motion estimation, and we adopt this practice in our work. Section Summary. In this section, we discuss various approaches to flow estimation, highlighting the limitations of supervised methods that rely on synthetic data and specialized architectures, and contrast them with our self-supervised Opt-CWM, which excels in real-world scenarios without heuristic dependencies. We also introduce our Counterfactual World Modeling (CWM) framework, which utilizes an RGB-conditioned next-frame predictor to effectively separate scene appearance from dynamics, enabling robust motion estimation and occlusion detection. Section: Optimizing Counterfactual Perturbations. In this section, we address the issue of optimizing counterfactual perturbations. We recognize that fixed, hand-designed perturbations, like colored squares, can sometimes help in analyzing motion with our RGB predictor, but they often fall short. This is mainly because they do not fit well with the specific context of the images and can lead to clear failures, such as the perturbation not moving with the object or being completely ignored. Using the challenging TAP-VID benchmark, we found that these original fixed perturbations are inadequate for effective self-supervised motion estimation. A good perturbation should be tailored to the specific image and position to create meaningful changes that can effectively probe our base predictor. The question then arises, how can we redesign these perturbations? Our approach includes two key innovations. First, we parameterize an image-conditioned counterfactual generator as a differentiable function. Second, we create a general-purpose self-supervised loss objective to learn the parameters of this counterfactual generation function. We reformulate the motion extraction process to be a parameterized differentiable function and introduce a class of perturbations based on a sum of colored Gaussians. We define a motion estimation function that takes an image pair and a pixel location, outputting the predicted flow, which is the difference between the estimated second frame pixel location and the original pixel location. This function involves several components: the counterfactual perturbation function that now generates variable perturbations based on the image pair and pixel location, the pre-trained RGB condition predictor, and a soft Argmax module that helps predict pixel locations using a differentiable method. We choose to represent the counterfactual perturbations as Gaussians because this method naturally creates in-domain counterfactual images. To determine the Gaussian parameters for a perturbation, we utilize the encoder from our RGB predictor, which provides feature tokens that capture both global and local scene information. For a given pixel location, we identify its corresponding patch embedding and use it to compute the Gaussian perturbation parameters. Next, we compute the difference image similarly to our previous method, ensuring that our function remains differentiable by using a soft Argmax instead of a traditional Argmax to estimate the pixel location in the second frame. Finally, we apply a temperature-scaled softmax to the difference image to find the expected pixel location for the second frame, allowing us to calculate the predicted flow. Section Summary. In this section, we address the limitations of fixed hand-designed perturbations for motion estimation, proposing a novel approach that utilizes parameterized Gaussian perturbations tailored to specific image contexts. Our method involves a differentiable counterfactual generator and a self-supervised loss objective, enabling more effective and context-dependent motion extraction. Section: Learning Optimized Counterfactuals. In this section, we explore how to learn the parameters of our perturbation generator. We aim to determine a self-supervised objective that makes the generator context-specific and produces accurate flow vectors. Our key insight is that we can effectively bootstrap this process by adapting the sparse asymmetric mask learning approach to a combined RGB flow prediction problem without needing labeled data. We train our counterfactual motion prediction function, which we call flow_theta, to estimate flow vectors, alongside a sparse flow condition predictor, psi_flow. This predictor uses a single frame and sparse flow vectors to forecast the next frame. We connect flow_theta's outputs to psi_flow as inputs and train them together using the reconstruction loss from the RGB predictions of psi_flow. Since psi_flow does not have access to any RGB data from the second frame, it can only minimize the reconstruction loss if the estimated flows are correct. For a given image pair, we use flow_theta to estimate motion for a set of pixels, resulting in a collection of forward flow vectors. We then have psi_flow, which takes the first frame and these estimated flows to predict the next frame. We optimize both flow_theta and psi_flow by minimizing the mean squared error between the predicted and actual next frame. To enhance our model, we implement a multi-mask strategy during inference, applying several random masks and averaging the results to mitigate the impact of any poor masks. We also refine flow predictions iteratively by applying flow_theta to smaller crops around the predicted point location from the previous iteration, which helps improve initial flow predictions. For evaluation, we use the TAP-VID Davis and kinetics datasets, along with the synthetic Kubrick dataset. We randomly select 30 videos for evaluation from TAP-VID kinetics and Kubrick. We conduct experiments under two protocols to assess performance in different scenarios. For flow methods lacking occlusion prediction, we utilize cycle consistency to identify occlusions based on inconsistencies in predictions. We also introduce a TAP-VID constant frame gap protocol, which uses a fixed 5-frame gap for fair comparisons with optical flow models. We compute metrics after rescaling predictions to a resolution of 256 by 256 pixels. Our evaluation metrics include average Jaccard, average distance, the average percentage of correctly predicted points within various pixel distance thresholds, occlusion accuracy, and occlusion F1 score to address the limited occlusion events in the dataset. Section Summary. In this section, we describe our approach to learning optimized counterfactuals by jointly training a motion prediction function and a flow-conditioned next-frame predictor without labeled data, leveraging end-to-end optimization to ensure accurate flow vectors. We also outline our evaluation protocols and metrics, which include tracking performance across various datasets and addressing challenges like occlusion prediction and frame gaps. Section: Baselines. In this section, we outline our evaluation protocol, which involves tracking points in videos through occlusion by establishing temporal correspondence. This means we determine where a point has moved or if it has been blocked in a pair of frames. To achieve this, we utilize both supervised and self-supervised optical flow methods, as well as self-supervised temporal correspondence methods. We implement several baselines. CWM estimates motion through counterfactual extractions with fixed changes, showing significant performance improvements over previous CWM methods. We provide a detailed analysis of this in a later section. GMRW is a recent self-supervised method for video correspondence, using a transformer-based architecture trained on cycle consistency with contrastive random walks. It excels in long-range tracking and serves as the state-of-the-art baseline for TAP-VID first. SMURF is an unsupervised method tailored for optical flow estimation, modifying the raft architecture to train with specific losses like photometric loss and smoothness regularization. It focuses on estimating motion between consecutive frames, using datasets like KITTI, Sintel, and flying chairs. Dodwo finds dense correspondences across images using unlabeled videos from YouTube VOS, employing photometric losses and the dyno encoder for sparse correspondence. However, it is not entirely unsupervised since it utilizes segments from Mask-2 former. C-Raft is a supervised flow method that enhances the original raft by adding pre-training on tartan air, a new mixture of Laplace loss, and better initialization for flow estimation. We present evaluation results on TAP-VID first and CFG in a table. Our top-performing model processes inputs at a resolution of 512 and is evaluated with 10 multi-masks and 4 multiscale iterations. On TAP-VID first, Opt-CWM surpasses all baselines across all metrics, particularly showing robustness in challenging scenarios with long frame gaps or high motion. On the CFG protocol, which favors flow methods, Opt-CWM either outperforms or competes well with the best unsupervised models, especially on Davis. We also provide qualitative comparisons between methods, highlighting that baselines struggle with videos that do not meet their heuristic assumptions, such as photometric similarity. Our experiments on the synthetic Kubrick dataset, which resembles synthetic optical flow training datasets, show that Opt-CWM performs best in this out-of-domain scenario among models not trained on Kubrick data. Additional qualitative examples of Opt-CWM can be found in the supplement. In our ablation and analysis, we compare Opt-CWM with various hard-coded perturbations, representing unoptimized CWM baselines, and find that learned interventions significantly outperform them. This indicates that the CWM framework is effective for unsupervised motion estimation and that optimizing counterfactual perturbations is crucial for strong performance. We illustrate the image-dependent nature of optimal predicted perturbations, showing how variations in Gaussian parameters depend on their placement in the image. This scene-dependent perturbation emerges from our training process and enhances flow predictions. We also observe that models with larger input resolutions perform better than those with smaller ones, and our multi-mask inference and multiscale refinement procedures greatly enhance performance. Regarding the distillation into a raft architecture, we note that Raft, C-Raft, and SMURF utilize a specialized flow architecture rather than large general-purpose vision transformers. To assess the impact of this design, we train a raft-type architecture using pseudo-labels generated by Opt-CWM. We label the motion for 1% of the pixels in a frame pair for each clip and train a C-Raft architecture on this pseudo-labeled dataset. Our findings indicate that this distilled model outperforms the self-supervised baseline SMURF and competes well with supervised techniques. This suggests that the key to Opt-CWM's improved performance lies in our novel optimized counterfactual extraction scheme and its flexibility to train on unrestricted data, rather than the architecture itself.